Discuss and derive the stationary value of a definite integral Euler-Lagrange's differential equation. Now let f is a function of f bracket starts y comma y dash comma x bracket close be defined on a path y is equal to yx between the two fixed values of x1 and x2, where y dash is equal to dy upon dx. We shall find out the particular path of a y star x such that the line integral of I is equal to integral x1 to x2 f bracket starts y comma y dash comma x bracket close dx has a stationary value. Thus we have y is equal to yx, yx is equal to y star x plus delta yx, where delta yx is a small variation in y. The quantity I is called as the functional of, as it is a function of the function yx. Let us represent the variation of delta y in the form of delta y is equal to alpha lambda x, where lambda x is a arbitrary function and alpha is a small parameter which does not depend upon x. Hence, for given lambda x, we can consider the curve to be a function of x and alpha, that is y bracket starts x comma alpha bracket close is equal to y star x plus alpha and x. For our convenience, it is assumed that both the correct path y star x and the oscillatory function lambda x are continuous and are non-singular between x1 and x2 with a continuous first and second order derivatives in the same interval. Also, let us assume that the variation at the endpoints is 0, that is lambda x1 lambda is equal to lambda x2 is 0 for any such a parametric family of curve. I is the function of alpha, that is I alpha is equal to integral x1 to x2 f of bracket starts y comma alpha x comma alpha bracket close comma y dash bracket starts x comma alpha bracket close comma x bracket close dx, and the condition for the arbitrary stationary value in delta I is equal to bracket starts di upon d alpha bracket close alpha is 0 d delta alpha which is 0, and this is equation 1. Now di upon d alpha is equal to d over d alpha integral x1 to x2 f of bracket starts y comma x comma alpha bracket close comma y dash x comma alpha bracket close x bracket close dx, which is equal to integral x1 to x2 del over del alpha square bracket starts f of bracket starts y bracket starts x comma alpha bracket close comma y dash bracket starts x comma alpha bracket close comma x square bracket close dx, which is equal to integral of x1 to x2 bracket starts del f over del y upon del alpha plus del f over del y dash upon del alpha bracket close dx square bracket starts, because x is not a function of alpha square bracket close. So integral x1 to x2 square bracket starts del f upon del y lambda x plus del f over del y dash lambda dash x square bracket close dx, and that is equal to integral 1 x1 to x2 del f upon del y lambda x dx plus integral x1 to x2 del f upon del y dash lambda dash x dx, which is equal to integral x1 to x2 del f upon del y lambda x dx plus square bracket starts del f upon del y dash lambda x square bracket close limit to x1 to x2 minus integral x1 to x2 d over dx bracket start del f upon del y dash bracket close lambda x dx, so which is equal to integral x1 to x2 del f upon del y lambda x dx plus 0 minus integral x1 to x2 d over dx bracket starts df over dy dash bracket close lambda x dx. Since lambda x1 is equal to 0 is lambda x2 square bracket close, which is equal to x1 to x2 del f upon del y lambda x dx minus integral x1 to x2 d over dx bracket start del f upon del y dash bracket close lambda x dx, which is equal to integral square bracket start del f upon del y minus d over dx bracket starts del f upon del y dash bracket close square bracket close lambda x dx, and therefore from the equation 1 we get integral x1 to x2 square bracket start del f upon del y minus d over dx bracket starts del f upon del y dash bracket close square bracket close lambda x dx is 0. Since lambda x is a arbitrary except for the restrictions upon continuity, and lambda x1 is equal to 0 is equal to lambda x2, therefore du f over dy is equal del f upon del y minus d over dx bracket starts del f upon del y dash bracket close is 0 for a curve y is equal to y star x, which gives the stationary value of I. The equation 2 is called the Euller-Lagrange's differential equations. Hence the integral I x1 to x2 f of y y comma y dash x bracket close dx will have the extremum if the integral f of bracket starts y comma y dash comma x bracket close satisfies the Euler-Lagrange's differential equation. Hence del f over del y minus d over dx bracket starts df on d del f on del y dash bracket close is equal to 0.